All right, so we're going to be looking at activity 15, which is dealing with quadrilaterals and their properties. And we're going to start off by looking at lesson 15.1, where we're going to be talking about kites and triangle midsegments. So we start off with Mr. Cortez, the owner of a tile store. He wants to create a database of all of the tiles that he sells in his store. All of his tiles are quadrilaterals, but he needs to learn the properties of different quadrilaterals so that he can correctly classify the tiles in his database. He begins by exploring convex quadrilaterals. And they tell you the term quadrilateral can be abbreviated as quad. So there are a couple of terms that we need to make sure that you know before we continue. Quadrilateral, that means that it has 4 sides. So any figure that has 4 sides is called a quadrilateral. Then convex. There are 2 terms, convex and concave. Concave is something that has an indentation. So there's an example of concave where there is an indentation. And convex means that it does not have an indentation. It is not concave. So the figure that they drew in your book, quadrilateral GEOM, is an example of a convex quadrilateral. So we're going to start off by looking at opposite versus consecutive to make sure that you understand those terms before we continue. So it says list all of the pairs of opposite sides. So opposite sides are ones that do not touch. They are not going to share any vertex. So you have GE and MO. And you also have GM and EO. They're on opposite sides of your quadrilateral. Then looking at pairs of consecutive sides. So these are ones that are going to be adjacent to each other. They're going to be right next to each other. GE and EO. EO and OM. OM and MG, and then G, MG, and GE. Those are your 4 pairs of consecutive sides. So we have 4 vertices here because we have a quadrilateral. There are 4 corners, 4 vertices. There are going to be 4 pairs of consecutive sides, the 2 sides that create each of those 4 vertices. So that's what we have listed. Then all of the pairs of opposite angles. So angles that are opposite of each other. Angle G and angle O, angle E and angle M. Those are opposite. They're not touching, they're across from each other. Your consecutive angles. Angle G and angle E, angle E and angle O and angle M and angle G. Your consecutive angles, if you connected those, would create a side. So G and E create a side, E and O create a side, etc. Those would make your 4 sides of your figure. Then the last part is to draw your diagonals and then list them. So when you draw a diagonal, that is connecting non-consecutive angles, non-adjacent angles. And so we have 2 diagonals, and they are EM and GO. And some people have asked, does the order of the letters here matter? No. Your variables and the order does not matter on these. You just got to make sure you have them paired appropriately. So that's opposite sides, consecutive sides, opposite angles, consecutive angles, and diagonals. And we're going to be using those terms throughout activity 15. So that's why they wanted to start with making sure you understood those concepts. So now we're going to look at a kite. A kite is a quadrilateral with exactly 2 distinct pairs of congruent consecutive sides. So this is important that you understand. If a quadrilateral is a kite, it has four sides that can be grouped exactly with two distinct pairs. So that's two different pairs of congruent consecutive sides. So if I have these sides congruent and I have these sides congruent, if this side and this side are congruent, and this side are congruent so that all four of them are the same, that is not a kite. With your kite, you have two sides that are congruent and you have two other sides that are congruent. These pairs cannot be the same. That's what it means when it says two distinct pairs. That's what creates a kite. And they also have to be consecutive. So if I have this side, and then this side and this side that are congruent, those are not consecutive. That's not going to create a kite. So that is a kite. Now we're going to look at number 2. They give us the quadrilateral KITE, and then they tell us KI is congruent to KE, and IT is congruent to ET. One of the diagonals divides the kite into two congruent triangles. And we want to draw that diagonal and then list the two congruent triangles. So the diagonal is KT. And the triangles that are going to be congruent are going to be KIT. So triangle KIT. And it's going to be congruent to triangle KET. The order does matter here because we're saying congruence. When you're dealing with a congruent statement, you do have to have the order in a specific way. And the reason that we know that they are congruent, they share the diagonal KT, which means that it's congruent to itself. And so these triangles are congruent by side, side, side. So now we're going to draw the other diagonal. And I'm going to draw it in green. And we want to explain how we know that they are perpendicular. How do we know that they form a right angle? So, in my figure, to start with, I have two angles that have a common vertex of K. Angle IK, I'll name this point A. So IKA. And angle EKA, and those angles are congruent by CPCTC. My triangles KIT and KET are congruent, and these two angles are corresponding angles in those triangles. And so that means that they have to be congruent. Corresponding parts of congruent triangles are congruent. Then I know that this segment here is shared by these two little triangles, and so they also have to be congruent. And so I know that triangle KAI is congruent to triangle KAE by side, angle, side. So this triangle and this triangle have to be congruent by side, angle, side. Side, angle, side. So I'm going to draw that as best I can. Side, angle, side. Then, if those are congruent triangles, then that means that this angle here and this angle have to be congruent. So I had said this was angle, or point A. So I have angle KAI has to be congruent to angle KAE by the CPCTC. And then if your two congruent angles form a linear pair, which they do, these angles create a straight line. They're supplementary. then they have to be right angles. Think about it. An angle plus an angle equals 180, where these are the same thing. Two angles equal 180. Your angle has to be 90 degrees. They have to be a right angle. And so since we have right angles that are formed, that's how we know that the diagonals are perpendicular. So KT is perpendicular to IE because we have right angles that are formed. So now we want to complete the list of properties of a kite. Think about the angles of the kite as well as the segments here. So they give us 3 of them. Exactly 2 pairs of consecutive sides are congruent. That's part of the definition they gave us to start with. 1 diagonal divides a kite into 2 congruent triangles. So that was the horizontal diagonal that we drew from K to T. It formed 2 congruent triangles here. The diagonals are going to be perpendicular. That's what we just looked at. Then another thing about the diagonals. So we have the horizontal diagonal. We can also draw the vertical diagonal. So that diagonal is going to cut the kite into 2 triangles, and it's going to be specific types of triangles. We know that KI and KE are congruent, and we know that IT and ET are congruent. And so both of those pairs of triangles are going to be isosceles. And that's going to happen every time. So the other diagonal divides the kite into 2 isosceles triangles. Then the other part is going to be dealing with the angles. So if you look, when we drew this diagonal, these angles are congruent because they're corresponding, and these angles are congruent. And so one of the properties is one diagonal bisects a pair of opposite angles. And then the other one is this angle I and angle E are corresponding and congruent. And so one property is that one pair of opposite angles are congruent angles. And that's going to be true for every kite. All 6 of those are always going to be true. So you're not going to have them memorized exactly word for word, but you need to know them so that if you're given those properties, you're able to recognize that you have a kite. Because they're not going to always say, okay, this quadrilateral is a kite. Sometimes they're going to give you parts of these, and they're going to expect you to recognize that it's a kite. So Mr. Cortez says that the diagonals of a kite bisect each other. Is he correct? Support your answer with a valid argument. So there are 2 different ways that you can work through this. One way, we know that the vertical diagonal is bisected. Those are the heights of congruent triangles, so we know they're congruent. But these are not congruent. And the reason that we know they're not congruent, these are isosceles triangles that I drew in red. If this was congruent to this one, then these sides would have to be congruent. And they're not able to be congruent because it's a kite, because that would force all of our sides to be congruent. So that's one way that you could work through and explain that it is not correct. that the diagonals bisect each other. You could say if the diagonals both bisected each other, then that would force all four sides to be congruent, and that does not fit the definition of a kite. You could also draw a kite on a coordinate grid. And so I'm just making up some points here. And so this is one diagonal, and this is the other one. As you can see, this diagonal length is 2, and this diagonal length is 2. So we know that these are congruent. We also know, since it's a kite, these sides are congruent, and these sides are congruent. Then we know the vertical diagonal has a length of 2 here and a length of 5 here, which are clearly not the same length. So the diagonals are not bisecting each other. So the horizontal diagonal was bisected because it was cut into 2 and 2 lengths. And then on the other diagonal, one is a length of 2, one's a length of 5. So there's an example showing that it doesn't work. So you could do either option. You could use the grid, or you could explain, whichever one you prefer. So now looking at number 4. Why is a square not considered a kite? There are a lot of different reasons that you could say here. But a kite does not have 4 congruent sides and 4 congruent angles. So it's not a square. Or you could say that a square has diagonals that bisect each other, and a kite does not. Or you could use exactly 2 pairs of consecutive sides are congruent. A square doesn't fit that. Any of the properties that a square has that a kite does not would classify as an option for why it's not considered a kite. You would not want to say a square has 4 sides, because a kite also has 4 sides. So that would not be a reason for number 4. You'd want to pick something that a square has that a kite does not have, or vice versa. Okay, so now we're going to look at AC and BD as the diagonals of a kite, and then we're going to look for the area formula for a kite using only that diagonals. So I'm going to draw a kite where we have AC and BD as the diagonals. And I'm going to start by finding the area of this upper triangle. So triangle area formula is 1/2 base times height. The base on this triangle is AC. The height of the triangle is half of B to D, because we know the length of BD, and we know that this segment here is half of that. And so that makes 1/2 times 1/2 is 1/4 AC times BD. Then for the triangle on the bottom, we know that those 2 triangles are congruent. That was part of the properties of a kite, that one of the diagonals cuts them in half. So if we double that area, 1/2 times 2 is, 1/4 times 2 is going to be 1/2. And so we're going to end up with 1/2 AC times BD. And so that would be the area formula for a kite in terms of the diagonals. If you know your diagonal lengths, multiply them and divide by 2. So now we're going to look at a mid-segment. So the segment whose endpoints are the midpoints of 2 sides of a triangle are called a mid-segment. So if you have a triangle and you have a midpoint of this side and you have a midpoint of this side, this segment here that connects those is the mid-segment. So then they tell us the triangle mid-segment theorem. The mid-segment of a triangle is always parallel to the third side and half of the length of the third side. And so we are going to actually complete a coordinate proof to prove the triangle mid-segment theorem. So first thing we're going to do is to start off with our hypothesis here. M is the midpoint of side AB. And N is the midpoint of side BC. If it's the mid-segment, then those are supposed to be the midpoints of their sides. And if that's true, the conclusion should be that it is parallel to the third side. So MN should be parallel to AC. And MN should be 1/2 of the length of AC. And so we are going to work through using the formulas that they gave us over here and hopefully prove that they're parallel in half of the length. So the first thing we want to do is to find the midpoint of M. So M's midpoint, x1 plus x2, our x values are a and b. So a plus b divided by 2. Our y values, y1 and y2, are h and k. So h plus k divided by 2. For n, our x values are b and c. So b plus c divided by 2. And our y values are k and l. So k plus l divided by 2. So those are your midpoints. You can't really simplify them past that. Now we're going to be looking for the slope. So the slope of AC, y2 minus y1 is going to give you L minus H over C minus A. The slope of MN is going to look a little funky. Our y2 is this K plus L over 2. Our y1 is H plus K over 2. Then our x2 is B plus C over 2. And our x1 is A plus B over 2. So that's what we get for the slope to start with. Part D asks you to simplify that and explain how your answer shows that they're parallel. So, first thing we're going to want to do here, your numerator has divided by 2. So we are going to start with K plus L minus H plus K is going to become minus H minus K, all over 2. We're going to combine those two fractions into 1. Same thing in the denominator. We have over 2, and so we have B plus C minus A plus B is going to become minus A minus B, because you have to distribute that negative. And so then K minus K cancels, leaving you with L minus H over 2. And then B minus B cancels, leaving you with C minus A over 2. From there, we're going to use, if you have a fraction divided by another fraction, you can make it multiplication and do the reciprocal of the second fraction, something that hopefully you remember from Algebra 1 last year. So we have two fractions that are being divided by. So L minus H over 2, instead of dividing, multiply by the reciprocal. So 2 over C minus A. And then these 2's cancel, leaving me with L minus H over C minus A, which is identical to the slope of AC, L minus H over C minus A. So the slope for both is the same. That means that they are parallel because they have the same slope. So we know they're parallel because they have the same slope. So now we want to prove the lengths of AC and MN, that MN is half of AC. We already proved they're parallel. Now we're trying to prove the lengths. So the first thing we're going to want to use is our distance formula for AC. So the square root of x2 minus x1 squared plus y2 minus y1 squared. So it's going to look in that form. And using your points A and C, your x values are C and A, and your y values are L and H. So that's what you have for the length of AC. For the length of MN, it's going to be in the same form, but your x values are going to look a little bit more funky. You're going to have B plus C over 2 minus A plus B over 2. And then K plus L over 2 minus H plus K over 2. And so by the same logic, whenever you simplify, B plus C minus A minus B, and K plus L minus H minus K over 2. Your B's are going to cancel, and your K's are going to cancel, leaving you with C minus A over 2 and L minus H over 2. And then, since we have a divide by 2, we can make that a 1/2. And you have to keep it squared because the divided by 2 was squared. And do you see how both of them have a 1/2 in common? And we're going to be able to take that out using the fact that the square root of x squared creates just x. You're left with whatever that is. So the square root of 1/2 squared is going to just leave a 1/2. And so we can pull it out of both of those terms to leave in the radical C minus A squared plus L minus H squared. And that is exactly what we had for AC, which means that MN is equal to half of AC. And so that shows the second part of the conclusion here that they were wanting us to get to. So all of that algebra work is proving the triangle midsegment theorem. No, you're probably not going to ever have to work through that 100% by yourself, but they were wanting you to try and prove it using a coordinate proof. So that's how it would work. So now we're going to look on the next page. Are the midsegments of an isosceles triangle congruent? Explain. So I'm going to draw an isosceles triangle. So this side length is 4. I'm going to say this side length is 5. It's not drawn exactly to scale, but just to make it a little bit easier rather than having radicals. So this is going to be the midsegment of this side, which means it's going to have to be 2 because it's half of 4. The midsegment for this one half of 5 is going to be 2.5. And the mid-segment for this left side is going to be over here, and it's going to be 2.5, because half of 5 is 2.5. Are all of those mid-segments the same? Obviously not. 2, 2.5, and 2.5 are not all three the same. 2 of them are the same, but it's either the mid-segments congruent. No. Only the ones that are parallel to the congruent sides are congruent. And that's always going to be the case. So if you had all 3 sides congruent, then yes, all 3 of your mid-segments would be the same length. But if only 2 of your sides of your triangle are congruent, only 2 of your mid-segments will be the same length. Then looking at number 8, DE and AC are parallel. So then it asks, is DE a mid-segment of triangle ABC? And so I want to go back to page 207 at the very top. A mid-segment whose endpoints are the midpoints of the sides of a triangle. Is D the midpoint of side AB? Are these 2 segments congruent? No, one's 5 and one's 6. They're not the same length. So is D a midpoint? No. Same thing with E. E does not cut side BC into 2 congruent pieces. So is it a mid-segment? No. And the reasoning is that DE does not bisect AB and BC. It doesn't cut those in half. So now looking at number 9, we have triangle PQR, and it gives us 2 mid-segments, AB and CB. And we want to verify the triangle mid-segment theorem using coordinates and the mid-segment AB. So we're going to start off with the slope. So we need to find the slope of AB and the slope of RP. Rise over run is -1/3. Rise over run is -2/6, which reduces to -1/3. So the slopes are the same, so that's good. Now we need to look at the distance, the length of them. So I am going to use this triangle here. It's a right triangle, and I'm going to use Pythagorean theorem. This side length is 1, and this side length is 3. And we're looking for the hypotenuse. So 1 squared plus 3 squared equals c squared. So 1 plus 9 equals c squared. 10 equals c squared. So we can take the square root, which means that the length of AB is the square root of 10. By the same logic, we can look at this triangle. This side length is 2, this side length is 6, and we're looking for the hypotenuse. So 2 squared plus 6 squared equals c squared. So 4 plus 36 equals c squared. 40 equals c squared. So the square root of 40 is our c, which is RP. But looking at it, I don't know if those are double exactly. And so we want to look at reducing that radical. So I have 40. If you take 40 and you factor it, you end up with 4 times 10. There are other ways that you could factor it. We're just trying to factor it. And it ends in a 0, so divide by 10, you get 4. 4 times 10 equals 40. 4 factors as 2 times 2. 10 factors as 2 times 5. So no matter how you factor to start with, you should end up with these 4 numbers. So 40, the square root of 40, can be written as 2 times 2 times 2 times 5. Anytime you're taking the square root, you have to have a pair of numbers to be able to pull them out. We have a pair of 2's, so I cross them out. 2 times 2 is 4, and the square root of 4 is 2. So whenever I have a pair, I'm going to take them out and put one of those on the outside. And then I'm left with a 2 and a 5, which don't have a pair, so 2 times 5 is 10. And so the square root of 40 reduces to 2 square roots of 10. And so obviously AB is half of RP. So we know AB is parallel to RP, and we know that AB is half of RP. And so we verified the triangle mid-segment theorem here for mid-segment AB. So now we want to do the same idea for part B. We need to look at the slope to start with. So the slope from C to B, we go up to the right 2. 2 over 2 is 1. The slope of R to Q, up 4, to the right 4. 4 over 4 reduces to 1. So that tells us that CB is parallel to RQ. Then we need to look at the lengths of them. So again, we can use Pythagorean theorem. If you prefer to use the distance formula, you absolutely can. I just think it takes a little bit more work here. So our triangle has lengths 2 and 2. So 2 squared plus 2 squared equals C squared. 4 plus 4 equals C squared. 8 equals C squared. So that means that the length of CB is the square root of 8. And 8 is 2 times 2 times 2. You have one pair of 2's, and you're left with a 2 on the inside. So the length of CB is 2 square roots of 2. For RQ, we have side length of 4 and 4, and our hypotenuse of C. So 4 squared plus 4 squared equals C squared. 16 plus 16 equals C squared. 32 equals C squared. And so we have the square root of 32 for RQ, which is going to be 2 times 2 times 2 times 2 times 2. We have one pair of 2's, and we have another pair of 2's. 2 times 2 creates a 4 outside of the radical. You multiply them. 2 times 2 makes that 4, and we're left with a square root of 2. And so as you can see, CB is half of the length of RQ. So that's verifying the triangle mid-segment theorem for those two. So now let's look at number 10. If XY is the mid-segment, that means that it's going to be half of 17. So that means it's going to be 8.5. It also means that X is the midpoint of this side, and Y is the midpoint of this side. So if XE is 6, DX also has to be 6. Then if DY is 4, that means that Y to F is also going to be 4. Looking at the next one, if QR is a mid-segment of the triangle, this is half of this one. So I can say 2 times 2x minus 2.5 equals 2x plus 7. And so I can distribute to make 4x minus 5 equals 2x plus 7. And then if I solve this for x, I end up getting that x equals 6. And so the first blank, x is 6. Then if I plug in for WZ, 2 times 6 is 12 plus 7 makes 19. And half of 19 is 9.5 for QR, or you can plug in 6. 2 times 6 is 12 minus 2.5 gives you the 9.5. Either way, you should get those values. Now looking at number 12. Figure ABCD is a kite with diagonal BD and AC. So that means that BD and AC are going to be perpendicular. That also means that triangle ABC is going to be congruent to triangle ADC. and that angle ABC is going to be congruent to angle ADC. That also means that AB and AD are congruent side lengths because they're adjacent and congruent. And then that also means that angle BAC is going to be congruent to angle DAC. That's using your properties of your kites. So hopefully that helps you a little bit with understanding your kites and triangle midsegments, dealing with activity 15.1.